control. So all of the different technologies that were evaluated in this had to maintain at least a 50-degree dew point. We're going to talk about that more. That's a very standard and an appropriate approach. So it's not, some crazy numbers that skew the values. They also required dry bulb temperatures of at least 68 in the dry goods and at least 60 in the refrigeration area. I would actually suggest those are low values. We never maintain low levels that much in a refrigerated area. We would definitely be in the winter at a minimum of 68 and, up to maybe 74. And I'm sure you'd agree with that. But this is the parameters they set for this study. They studied, unfortunately, they are an American institution. I'm out of Toronto, by the way, so I'm a Canadian. Everything centers around the U.S. when it comes to the Department of Energy. So they studied 6 regions in the U.S. Some of them definitely capture where we live and the majority of the Canadian population lives, but 1A through 6A, and you can see the stars of the specific cities that were used for the climatic conditions. And so the highlights are they looked at this in kind of 2 rounds of studies. They set a baseline. The baseline was kitchen exhaust with makeup air units that were, dynamically controlled integrated to it. So kind of the very best in class of how to deal with kitchen exhaust. You guys have done some kitchen systems and kitchen exhaust systems, I'm sure, right, in some of your projects? Yep. All right, great. So, the kind of this is kind of mainstream these days, but what they essentially concluded is you want to have 90% of your exhaust made up by local makeup air units, and then 10% of that transferred in from the sales floor. So that's what they set as the baseline as the best in class. And again, there's a whole study in this report about what that looks like and the different energy benefits. In comparison to that as the baseline, and then on the sales floor, by the way, the baseline was just like RTUs, standard rooftop units, cooling, and attempting to dehumidify the sales floor area. So some of the more advanced technologies they looked at were a DOAS unit, a DX DOAS unit, feeding into a return or an RTU. So actually a combinational ducting system, very kind of complicated. Nobody actually does it in the real world, but that's one of the ones they compared to. You guys know, of course, the term DOAS stands for dedicated outside air unit, right? And so a DOAS unit is intended to be a unit that brings in all of the outside air that's needed for the space through itself. It's a unit that's dedicated to outside air management. They also studied DOAS units with single path units used around it. So just recirculating units. So a unit that brought the outside air in and units that do the recirculation in conjunction. They studied a product that is an internal dehumidifier. You might have a dehumidifier at your house, maybe in your basement or somewhere, and essentially it just sits within the space and it dehumidifies the air within the space. Then they also looked at some more advanced dehumidification systems, variable capacity RTUs. This would be things like your more advanced rooftop units, like maybe a Weathermaker, or certainly a unit with a reheat coil and a strong dehumidification capability. So very powerful and capable units on that side. This is us. They call it the adaptable multipath unit in the study, or the adaptable unit. And so they had our unit, and then they had single path units in conjunction with it. They also studied single solid desiccant units. You may have come across desiccant dehumidifiers in the past. They did desiccant units feeding into RTUs. They had liquid desiccant units, internal, and liquid desiccants as well. The liquid desiccant company that was used in this study is no longer there because the solid desiccant unit company bought them up and shelved their technology, so it never saw the light of day sometime after the study happened. And that's what happens in the real world. So unfortunately, that is not even available as an option, but it's in the study. So I thought I'd include that. Please. So desiccant is an approach to dehumidification where essentially you use almost like an ERV wheel, if you want to picture it that way. And it has, kind of microscopic sieve, and it uses vapor pressure and vapor gradient to draw moisture out of one airstream and deposit into another airstream. And so what they do is they take the moisture out of the outside air before letting it go into the space, and they bring another airstream through the other side that absorbs that moisture and exhausts it to the outdoor air. If you've never come across one of them, you're probably lucky, because they can be a massive headache from a maintenance, a service, a degradation standpoint. But where you will find them is you'll find them in lithium battery manufacturing, very, very low dew point applications, because it is a very powerful dehumidifier. So you can get dew points down to like 5 degrees, 10 degrees Fahrenheit in some of those. And those factories require that because, as you know, lithium water doesn't mix too well. Does that answer that question? Yeah, yeah, absolutely. There was a company in the industry that did quite a bit of those, and a few years ago they kind of pulled back, but they are still out there. All right. So the results. This is the Climate 1A, which, if you remember, was Miami area. And this is how the results come out. So the dough as examples, these are some products you may have come across. These are very popular in the US, and they performed 17% better than the baseline. The energy study looked at HVAC cooling energy, HVAC heating energy, and refrigeration energy. So it's looking at all of the energy factors that can be impacted by HVAC. The internal dehumidifier was there, and it was a 14% improvement over the baseline. Then you have variable capacity units like a captive air RTU, Seasons 4 RTU, Carrier Weathermaker would be in that class. They fall into the 18%, and then the solid desiccant being 10%. And of course, yours truly here, the adaptive multipath unit is there, saving 36% over the baseline. So Florida is a good place to use us. Fortunately, you guys aren't in Florida or designing for Florida, I don't think. So you want to see what the rest of the map looks like. So this is the rest of the regions. Looking at region 1A through to 6A, you can see that the adaptive multipath saved more energy than all of the other technologies across all of the regions. And I've got Jerome looking sideways to see if he can read some of the labels. And I will definitely send this to you. This one's a bit of an eye chart. Look at the bright yellow highlight and you can kind of see. But you can see the differential changes. So in Climate 1A, for example, the savings over the RTU approach is $39,000 of energy a year. So it's pretty significant in 1A. As we move all the way up to there, we have 18,000, 16,000, 12,000. 6A, I think, is 10,000 savings over the next best option. So still good savings in all of these cases. These numbers become significant when we look at these different factors. And NREL's conclusion, this is right out of the report, is the adaptive multipath demonstrates substantial savings in all climates. And it's not surprising just because of the way we integrate technologies from the other technologies that are out there. So we love this report. Nobody else in the industry likes this report. You'll never see it. You will never see it from anyone else. But it is a public report. You can get it right off of NREL's website. Any questions? All right. Yes. Mhm. No. So the baseline is the kitchen pretty much taking care of itself with makeup air units. However, a deficit or a negative pressure of 10%. So the sales floor units, that in this case would be our unit, and as needed, some single path recirculation units, because sometimes you need those accessory units, right? We would provide that missing air as what we call transfer air. So essentially, whatever that CFM, that 10% equates to, we bring in that additional outside air. And the reason is of course, you want the seafood smells to stay in the seafood department. You want, all of those things. You want that air transferring, because if you don't do that, then, you're going to get those things coming back into the sales floor that you don't want. Yeah. Yeah. Yeah, absolutely, absolutely. That's best in class design. I do find I was asking somebody the other day, why do bakeries often not have exhaust? And I think the answer is they actually want the smell from the bakery to work its way back into the store. They don't want the seafood. And I was in a store just a month ago, and I could smell the seafood department from the other side of the store. And I was like, all right, I got a problem here right away. And it's one of our competitors' units. Good question. Hmm. 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 Okay. Okay. That's okay. That's a design. Again, we see how much CFM again? Okay, it's not a lot. It's not a lot. Okay. Yeah, it depends on the size of the store. I mean, if you had a really large seafood area, and the CFM was enormous, then some people will consider doing a more localized makeup air unit. The reason that it's different is a makeup air unit doesn't bring the air down to the perfect environment for the rest of the store. So it might do some cooling, maybe some dehumidification, but usually just a bit of cooling, because that air is going to be exhausted right away again. right? So why would you put a whole lot of energy into making that air perfect just to pump it out of the building? Whereas if you have our unit providing that, we need to bring that air down to the right humidity and the right temperature for the store, the people, and the refrigeration cases. And so, you want to limit how much of that energy you put into that air just to transfer it and exhaust it. 1500 CFM, probably not a big deal. But if you're up in the 4000, kind of CFM, there's a lot more energy being maybe needlessly, consumed there. Does that make sense? Yeah,
And Peter's answer is exactly why Dave Bradley likes to put an extra little makeup air unit on the side to cover those. But we can also do a contact and tie the exhaust air into our unit as well, so
that's
that
right.
we can drop down as well. So
Yes, that's definitely very wise. Yeah. Hmm. I'm apologize. I don't know the HMAR layout too well. You have a seafood department. What other kinds of food prep, kitchen exhaust type areas do you have? Sure. That'd be great. Yeah, why not? Thank you. I'll stop sharing, but I think you probably can take control. It's your meeting.
Mhm.
Wow. We can.
Mhm.
Yes. Hmm. Wow.
Are those water pipes that we're seeing in orange and red? Oh, oh,
Oh,
it's
wow.
ductwork. Okay.
Hmm. Okay. 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 Right. Hmm. Mm-hmm. Mm-hmm.
Mm.
Hmm. Uh-huh.
Hmm.
Right. 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 Okay. Good. Mhm. Right. Yep. Yep. It's like fun. Hmm. Right. Right. Well, that's it. And mhm. Ba- okay. Okay. And you just said the word heat pumps. Sorry, you have heat pumps units as well in here? Hmm. Hmm. Okay. Hmm. Right. Right. Hmm. Hmm.
So they're
Okay.
water cooled heat pumps. Nice.
Okay.
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 Mhm.
Do be cautious. I see you're bringing you. I think you said some outside air to some of those heat pump units. I couldn't quite tell, but I see one of them at least, maybe a couple. Um, mhm, 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 mhm. Okay. Right. Okay. And yeah, it's always about balances. We'll talk about it a little bit later here today, but as you're probably aware, heat pumps hate outside air, or at least air source heat pumps, water source heat pumps, and ground source heat pumps do. Refrigeration source heat pumps actually like it, but those other types of heat pumps, you will find that they will shut out at a much higher temperature. And when they're water source heat pumps, the coil, the coil that's drawing the heat, it's happy because you're giving it reasonably temperatured water, but the inside coil, the one that on a heat pump is going to be releasing the heat into the space, you will find that your heat pump shut off at higher ambient temperatures because you're giving them that cold air. They don't like that cold air, and you lose efficiency as well. So certainly something to consider. We often encourage people to make their heat pumps recirculating only air units, but if you're not aware of that, something to be considered. Hmm. Hmm.
Mm.
Hmm. Yeah, absolutely. Yep. Right. Yep. Okay. Awesome. Hey, that looks great. No, thank you for sharing that. That helps a lot. I'll try and emphasize those things as we go too. And I'm sure there's lots more we'll talk about beyond just this. This is a good overview today, but I think there's more to be covered when you get to that level of detail. All right, so just going ahead of this next slide, we're going to talk about sources of moisture. So none of the CES people can answer this question, but Kelvin, and Dimitri and Jerome, what are the four most significant sources of moisture or humidity in a grocery store or for a grocery store?
Sorry, could you repeat that, please?
Absolutely, absolutely. What are the four most significant sources of moisture in a
Oh,
grocery store or for a grocery store?
people,
Humidity.
food,
Hmm.
um, the refrigerators or the cases,
Okay.
and
The outside air.
Ooh, good answer. Outside air.
yeah.
I like him. Thank you. I like the other answers too. Sorry, I didn't mean to
No, it's okay.
say. Outside air is number one. No question about it.
Yeah.
It is 75% to 85% of what we call the latent load. Of course, you guys are all mechanical, so you know what that word means. It's our moisture load, and it's coming from the outside. And so that's number one. So let's hear about some of the other ones. I'll give you some. I think I heard like kind of like food. It's a little further down the list. I would say the next one would be people. People are your next largest source of latent load. And of course, they're inside the store. So you have your outside air coming in from the outside, you have your people on the inside. So they're an internal source of latent load. They're 10 to 20%. And again, this is when we do our load calculations based on ASHRAE's 62.1 guidelines for what we have to do in terms of capacities for handling, peak loading of people. The next one actually is infiltration, and that one's one that people don't usually pick up on, but it's a pretty significant one, especially if we don't positively pressurize our stores correctly. And of course, that whole transfer air discussion we just had with makeup air, that all fits into that equation as well. It also depends on how old your building is, whether you have vestibules, these kinds of things. One thing we see, unfortunately, quite a bit is we see contractors, especially in the South, they see a store that maybe feels a little bit too humid, and they go and they screw down the outside air dampers because they think the source of their moisture is the outside air, and it is. But if you shut down the machine that's going to bring it in, where does it come from? Well, it just comes through the walls, it comes through the docks, it comes through the front door. And now you have untreated humid air flooding into your store, going right to your refrigerated cases. So that's the wrong approach to that situation, of course. Infiltration is that. And then the last one, actually, it's interesting, is that food the kitchen equipment, the misting equipment, generally they don't make up a large portion. It's amazing only because the other ones are so much more significant. But those are the four most significant. Now, one, I think I also heard refrigeration is actually a dehumidifier. A refrigeration case will generally remove moisture from the air, but we don't want it to do that because how does it do it? Well, it freezes that water on its coils. And that's not a good thing. So refrigeration equipment is playing a role, but it's not creating moisture. It is potentially removing it if we don't do our jobs properly. Does that make sense? All right.
Yes, it does.
Great. So now let's look at psychometrics. Oh, exciting. How much fun can we have today? Psychometrics, you guys know this stuff. I forgot it years ago, but when I came back to the HVAC world, I've had to relearn it. So temperature across the bottom, no horizontal, right? That's our temperature line. It goes up as we go horizontally to the right and down as we go horizontally to the left. Moisture is the one that's tricky. So moisture is represented on a psychometric vertically, but it's absolute moisture that's represented vertically. You guys know what relative humidity is, of course. And relative humidity is shown as these curves. And so we really don't like to think about relative humidity when we're thinking about moisture in a grocery store because relative humidity changes with temperature and absolute moisture. So as a simple example of that, let's say if I have, I don't know, let's take 50 degree dew point, or essentially a dew point temperature of 50, where the moisture would condense. If we heat that air up, then we get a lower relative humidity. So the relative humidity drops because the air can hold more moisture. And so it may seem like warming air up dehumidifies, but it doesn't. All it does is it creates more capacity, which is what humans think about because it's all about how much our skin evaporates water. So that capacity matters. But to a refrigeration equipment, its coil is at a fixed temperature. Your freezers are sitting at minus 30 Fahrenheit or whatever the case is. They don't care about the capacity of the air to hold moisture. All they care about is at what temperature is that moisture going to condense and freeze on that coil. And so we always use relative humidity, absolute humidity. I was looking for somebody to stop me there, because that is what matters to the equipment. And so we use different measures for that. The most common is dew point. Dew point temperature is our measure that we use for absolute humidity. You could also use grains of moisture per pound of air, different factors like that. But that's a really important concept. Anybody disagree? Everybody with me on that? Do you guys in your designs think in dew point, or are you thinking in relative humidity for your other applications typically?
I'd say more in relative humidity. I mean, we deal with like dry bulb and wet bulb temperatures,
Sure.
but we don't like specify too much about the dew point.
Okay. Okay.
That's more for the residential stuff rather than.
Absolutely. Yeah. Human comfort, right? Because it's all
Mhm.
about the relativeness of it. Absolutely. That's a perfect way to go about it. Yep. Okay. Well, we want to make sure that in grocery, you're always thinking about dew point and working in that terms. So why does this matter? Well, the energy required to remove moisture from the air in a grocery, we really have three ways of doing it. It can be the low temperature cases, your freezers. They need the most amount of energy to do that. They're just not made for removing moisture. That is not their purpose. The medium temperature cases, you could use them as well. And that alpha happens in bad designs. Or you can let the air conditioning do it. And the air conditioning is the most efficient way to remove moisture. And of course, the reason is that we don't let the moisture freeze on our coil. We don't have to run to those low temperatures. We maintain our coil at the optimal point to pull moisture out without freezing and having to defrost our coil and all these things. So that's why we're the most efficient at it. And that is our purpose. We're probably the only vendor you'll come across that doesn't think we're the most important piece of equipment in a grocery store. It is the refrigeration rack. It really is. And the refrigeration cases. Our job is to make that work properly and keep the people happy and shopping and spending money and not running out of the store because it's too cold, which is a common problem. ASHRAE recommends a 50 to 52 degree dew point as the optimal for stores. This is the point at which we're using the least amount of HVAC energy to save the most amount of refrigeration energy. If we make it drier, we need to spend more energy to make it drier, and the refrigeration system will save a little more energy, but not as much. And so there's this crossover point. And if we don't dehumidify to this level, the refrigeration equipment's energy goes up exponentially. And actually, 55 dew point is the warranty limit for refrigeration equipment. If you read their fine print, anything above that is outside of warranty operation for refrigeration equipment. So we have to stay below that. You, Jerome, I saw you just thinking, or Calvin. Yeah, go ahead, please. Yeah, it freezes up their coils. So their coils are running at, just above freezing, and I'm sorry, I had to relearn Fahrenheit. I mean, I'm a Canadian. Naturally, I think Celsius, but I've had to relearn Fahrenheit in this industry. So, they're running their temperature to those cases at like what, 35 Fahrenheit, just above freezing for their dairy and meat. And then their frozen goods, are minus 20 kind of range. Their coils are even colder, of course, to create that environment. And so, as you can imagine, a 50-degree dew point, pretty much those coils are always going to see moisture condensing on them. If it's higher, it just gets worse. And so they're designed to operate in an environment less than 55 dew point. And if you operate them above, you're outside of their warranty. Does that explain that? So it's really about freezing their coils, in which case they have to defrost. And you probably in refrigeration equipment know about the defrost cycles. The more frost we create on their coils, the more often they have to defrost. And so their defrost cycles go up, which means they're expending more energy to actually freeze them, thaw them, remove that moisture, and the cycle repeats. Yeah, no problem. Yep. All the refrigeration vendors get this. Almost none of the HVAC companies think about this because it's just such a small little application in the world of HVAC, isn't it? Grocery stores, but it's your specialty and it's definitely our specialty. Yeah. All right, moving along. So let me talk about the evolution of how we came to our product called a DOAS Plus. So we start with a most basic unit, a single path unit. I call it SPU. And essentially, you would think of it as a recirculating unit. It's a unit that takes the return air, brings it up, comes across a coil, might be cooled a bit, and then it's sent back into the space. Pretty basic unit, right? If you look at the psychometrics of this unit, what it's doing is essentially it is cooling air, right? It's taking it from this point over to this point. It's not doing any dehumidification because, as you notice, that line is horizontal. There's no vertical movement in that line. So this is purely doing cooling, at least in this example. This isn't okay for a grocery store or for really any application on its own because we also need to bring in outside air. We have 62.1 IAQ requirements to bring in a certain amount of ventilated air. And in your case as well, for these stores, we have some makeup air that we have to provide for some of the exhaust sources as well. And so this unit isn't okay alone. What we need to do and what the industry will often do is they will bring some outside air into these units. And so we call this a mixed air unit. It's in a single path with outside air. You might call them RTUs, rooftop units, but that's not really the right technical name because everything that goes on the rooftop is a rooftop unit. So we kind of call these mixed air units. And essentially you bring in some of the outside air, it mixes, then it goes across the coil and it returns to the space. What's interesting to note is when we look at the psychometric for that, is that the outside air, in this example, this is Toronto, by the way, where I pulled these ones from, on a peak day, is really hot and quite humid. It's over by the saturation line. And then you have your return air from the store down here. When you mix them together, this hot, humid air is pulled down, actually away from the saturation line. It's mixed. And then both those air streams go through the coil and are cooled, right? What's difficult about this is you have a large volume of air. You have all the outside air and you have all the return air going across this coil. And as you may know, coils don't really, they're more effective when we limit the amount of air over them, especially when it comes to dehumidification. We want that air to kind of dwell on the coil so that the moisture comes out. I was at a unit yesterday down in Baltimore I was at, and it's just great to see that water just pouring off the coil because the air has enough dwell time on the coil that really cools it down. The humidity just comes falling out of it. Some of our stores, actually some of our small customers, we remove 150 pounds of water an hour from the air. Just give you a sense, right? This is not a small amount of water that's coming out of here. But these units struggle because they've got a limited coil and they have a lot of air crossing that coil. So that's a difficulty for them. So this is not really the best way to do it for a supermarket.
Here's a quick question.
Yeah, please.
What's the absolute moisture that you're kind of looking at for like to get
To get
the
to?
air to? Yeah.
Yeah. So we want to get between 50 and 50. So 50 and 52 dew point, which is a measure of absolute moisture level. I don't know what the grains are. That sounds like, anyone know the grains? I think it's like 55 grains, maybe 57 grains. My brain's not a very good psychometric calculator. Yeah, does that answer that question? Yeah, that's the level that we're looking for. Are you looking for a different unit?
No, I'm just kind of wondering, just like the whole refrigeration process or the coils and stuff like that, just kind of getting
Yeah.
some numbers for me.
Yeah, so we will drive. So when we're in dehumidification mode, depending on the level of humidity that we are dealing with, we will drive the coil all the way down even to 35 degrees. So the refrigerant and the coil, the section temperature, if you want to call it that, is down to 35. So the coil is very cold. What we're trying to achieve is a store that is sitting at between about 50 and 52. That's the dew point temperature of the store. That's kind of what we want because we want to be below the 55, which is the high limit for refrigeration equipment.
Okay.
So we drive our coil really cold. We get as much
Yeah.
moisture as we can, and then we get it back to this bar. Keep going. Yeah. What do you think?
So like on the
Mhm.
dehumidification process, like you're cooling
Mhm.
the air to get the moisture out, and then
Mhm.
don't we have to reheat the air
Absolutely.
back up to it?
Oh, I love it.
Yeah.
The next slide.
Okay.
That's good. I love it. Good
Yeah.
thinking. Exactly. So as you can see, actually, it's not even the next slide. It's the next click on the slide. This air here in this case, if you push or you have enough capacity, even with these mixed air units, if you push them hard enough, you can get them to the saturation line and then you can start getting moisture to come out of the air. And that's what we see in this purple curve here, right? That's starting to dehumidify. And then as you mentioned, you can't drop air back into a space at 55 degrees because, or even lower at times, because if the ambient air has a higher moisture level, what's going to happen? All your ducts are going to sweat. You're going to have dripping off of your ceiling, and obviously you're going to get other problems with your cases. So what we do in these units, we put in a reheat coil. That's exactly what I think you were talking about. That coil is there to essentially temper the air, to bring it back up to a kind of a neutral temperature that we can deliver it to the store. And so in this case, and some of the ASHRAE standards require that you have the capacity to get it back up to 70 degrees. Now, we don't actually need to get all the way to 70, but the units have to have that capacity to do so. And so this is the cycle. You're right. You are cooling, dehumidifying, and reheating to get it back up to a neutral point. So this unit, if you just look at some of these values, it looks like this unit, the incoming air is at about 58 dew point, because see, it's just a little bit below the 60, because these are the dew point numbers there. And then in this psychometric, the unit is driving that air down to 54 dew point, and then it's reheating it, and it's still at 54, right? So 54 isn't acceptable, is it? We said that what we really want is 50 to 52. So these units generally can never dehumidify enough to keep a store happy, which is why you find if you try and apply these units to a grocery store, you have all of the humidity problems with the cases that everybody is always afraid of. And so these units are really just not sufficient for this job, but that's how they operate. Does that make sense, Jerome, to your question?
Yeah. No, that
Okay,
makes perfect
absolutely.
sense.
All right. So put that one aside. Because of this lack of sufficiency, what the world did is they came up with these DOAS units, dedicated outdoor air system. And a DOAS unit takes the outside air and only the outside air goes across the coil. The benefit of this is you have a relatively small amount of moisture that's spending a lot of time on usually a really big coil, by the way. These are usually like 6-row coils. And so you're really able to get the moisture out. And when you look at the psychometric of it, you see it makes sense. The outdoor air is just drawn right down along the saturation curve. Moisture is just pouring out of it. And then we add whatever reheat we need to do to bring it back up to a tempered temperature. So you can see this improvement and advantage that this thing has as a dehumidification. What I'm not doing is I'm not talking about these numbers here, but on here I actually have numbers for the energy, the MBH of energy needed in these different processes. And this one's now gotten quite small, but this is significantly better than these other ways of taking moisture out of air. So that's your DOAS unit. Now a DOAS unit, you can't have that on its own because it's only doing outside air. So we find DOAS units often put with recirculating units. That's that SPUs I was talking about before. And you have this guy dealing with the outside air, and you have this guy dealing with the recirculating air, right? Makes sense. But when we look closely at this, and I'm going to zoom in here, you see that you've got your DOAS that's cooling and dehumidifying, then it's reheating. And over here, you've got this single path unit that's putting in energy to cool. And these two things are going in opposite directions. And whenever I see things working in opposite directions from a psychometric standpoint, I see opportunity because in some ways there's waste here. This RTU is cooling the reheated air coming off of this DOAS. That's actually what it's doing. And so this is where we came up with something called DOAS Plus. This is still the same concept of DOAS. The outside air is going over the in coil. And if I look at the psychometric, It's the same curve here. We're dehumidifying the outside air. But now what we're doing is we're bringing the return air around the coil. We call it a bypass, and we mix it after the coil. And by doing so, we get passive reheat of our dehumidified air, and we get free cooling of our return air. Because the byproduct of a dehumidification coil is cold, dry air. So instead of reheating it and dumping it into the store, why don't I use that cold air to cool my recirculation air? And so that's what we do. That is the core thing about what is special about our product. This is patented technology. It's very simple in concept, but very powerful in its ability to do things. And so we really minimize our need for reheat, and we get all of this extra free cooling. So in many projects where I maybe see a 30-ton DOAS and a 6-ton RTU, we do it in a 30-ton DOAS plus. We get 6 tons of free cooling. We just wipe that unit right away. Don't even need it, because we're leveraging our free cooling capacity that what we have. Any questions to this point? Because this is a key concept as to what we do and why our product is special. Nope. All right. Yeah, and we can talk again. Now, what the obvious objection is, and I'm always looking for objections, is, okay, but hold on, Peter, what happens if that return air needs some additional cooling itself, or some additional dehumidification or something of that sort, because I'm bypassing it? So our company, we never just leave it here. We take it even another step. So our product is actually considered a DOAS Plus with adaptive multipath technology. We have this other set of dampers that allows us at times to also bring up some of that return air and put it across the coil. Now, what that means is we're getting less dehumidification capacity out of the coil because there's more air now going across it, but we're getting more sensible or cooling capacity out of the system as a whole. You can't have it doing all of those things at once. Unfortunately, we don't need it to. So there's no psychometric for this. Instead, I'm going to show you an animation on the next slide that'll explain how we use these different dampers in different operational modes. And that'll be this next thing. So this is an animation of how our unit works. On the upper right-hand side, I'm not so good with my right and left, sorry. In my upper right-hand side, I have a graph. And in this graph, you'll see the moisture load, which is in blue, of a store. And you'll see the sensible or the heat or the cooling load demand of a store as well through the course of a day. What you'll notice is that in the middle of the night, between midnight and 5 a.m., our moisture load's pretty constant, and our thermal load or our sensible load is declining because it's cool outside. Typically, the store's temperature actually would likely fall at that case. When the store opens, we go into an occupied mode. And as soon as that happens, we need outside air. As you guys know, when you have occupancy, you need ventilation air. And it's that ventilation air that suddenly makes our humidity load pop or jump, because we're suddenly bringing in outside air. So all of a sudden our moisture load goes up, but our heat load is still quite low. And so this is our dehumidification. Then through the course of the day, as more people come in, the day gets warmer. Now we have more heating load or more sensible load. And then at this point in the day, let's say a cold front goes by or something happens and we lose our moisture load. Now we have nothing but a cooling load. So I'm going to show you what those different points look like. So we start off in unoccupied mode. We bring in our return air only. It's coming up over the coil. Maybe the coil's on, maybe it's off, depends what the air needs. We run our fan at half speed because we're just doing recirculation of the store, and that's just cycling that air around. That's that beginning of the day. But as soon as people come into the store, maybe the staff, maybe early shoppers, we have to have ventilation. And so our outside air damper opens, and now you get this inrush of hot, humid air, or not hot necessarily, but at least humid air from the outdoor. And this is when we go into the DOAS Plus configuration. We bypass our return air, we focus our coil on dehumidification, we take all the moisture out, and then we mix it afterwards. Now, this coil you'll see here, this is a reheat coil or a reclaim coil. We do use this at coil at times to also add or temper the air, because sometimes there's just so much dehumidification going on, we can't temper it enough with our bypass, in which case we need to lift that temperature a bit. So we have that there as a tool in our toolbox. Our fan speed has increased to 80% in this case, and you'll see that through these different modes, our fan speed will change. The reason it's changing is as we adjust these dampers, we're changing the static pressures within the unit. And so because we have different channels the air is flowing through. And our number one goal, what we need to do is we need to maintain a constant outdoor air volume, because that's our IEQ requirement. And you guys will set that for us. Because Kelvin, you're going to say, Flo needs to provide this much outside air, Some of it's IAQ, some of it's transfer air for your makeup, for your seafood area or whatever, but you're going to define that, and we need to make sure that we always give that to you. So watch that number. You'll see that it stays constant in all of our modes, and that's one of our key goals and our deliverables. So that's our dehum mode. As we go further in the day and we see that, okay, we don't need quite as much dehumidification, we need more cooling, this is where we go into a mixed mode where we let a little bit more of this return air to come up over the coil. And so we get more cooling capacity, slightly less dehumidification capacity. Again, it all depends how much air we let come up here. Now we're running our fan speed at 90% just because of our static loads and static pressures, but we're maintaining a constant outdoor air volume. And then the last mode, of course, is cooling mode. If we get to this case where we have no dehumidification need, but we need a lot of heating or cooling capability, then we'll bring all of our air streams together. This is very much like that single path unit with outside air, right? Just a mixed air unit at that point. So we have the capacity to be, or the capability to be just like those other units when it's appropriate for the unit. Fan speed's 100% at this point, and again, maintaining our constant outdoor air volume. The one time that we can change our outside air volume, and again, we need to arrange that with you, is if you want demand control ventilation. So if there's an opportunity because the store is not occupied by a lot of people and the CO2 levels in the air go down, then we have the option, of course, of putting DCV in place, and that will close down our outside damper by up to 10%, and that'll reduce the outside air. Now, that's something we need to work out with you in advance because we need to make sure, of course, that we never go below your exhaust volume of air that you need as well for your seafood and all these other kinds of things. But that's an option there. And of course, that saves energy. Questions to this point? These are our cooling and dehumidification modes of operation.
Yeah, I have one question.
Adrian.
Where did you get that table from in the upper right corner? How's that determined?
Oh, so it's kind of an example of a kind of day. It's not like pure data from a place. It's just to kind of help people understand how the loads change in the course of a day. Why do you recognize it from somewhere? I didn't steal it from
I
anyone.
just was curious because it's really really interesting.
Yeah. I mean, it's based off of data from stores, but for example, I took the latent load at 3 p.m. and I cut it right out of the data and dropped it down because I wanted to demonstrate the circumstance where we only have cooling. Probably in most stores, there's probably a more gradual cooling front, cold front weather patterns can happen. But I mean,
of course, different areas as well.
If your store emptied out and your kitchen shut down, I guess you could lose some of your latent load. I don't know. That's where I got it from, though.
Okay, well, it's a good example. I like it.
Good. Thank you.
I understand it.
Great. One thing to, of course, point out is we're just showing you the dynamic nature in the course of a day. But this dynamic nature exists in the course of different seasons, right? Your winter time is not going to have humidity, but your summertime is. Your shoulder seasons are going to be different. And then the different regions across North America experience the same kind of variation. So you put this unit in the desert, it's never going to be in dehumidification mode. It's always going to be in cooling mode, right? But you put this anywhere on the eastern coast or down to Florida, it's always going to be in dehumidification mode, or at least all the times when that matters. And so it's this adaptability. And when you go back to that NREL report that shows that our unit is superior in all the regions, it's for this reason, because the unit adapts to the load combination that is required for the store and that it's getting from the outside environment, whether that's the course of the day, the course of the season, or the course of the climatic region. So most of our customers will say, we want this unit in every region because they know it is optimized for whatever region they drop it in. And same thing with your customers that use us. Okay. Yeah. So Barb could probably answer that best, but we can use chilled water on this coil, of course, if you have a chilled water supply. What's the ideal temperature we like, Barb? I want to say kind of 40, but
we've done 44 to 54, 42 to 52, 40, like.
Really? In dehumidification?
Oh, sorry. That yes.
Chilled water.
Chilled water that they provide to us because we're pretty limited, so we don't get as tight. Obviously, the higher they go, but
we like it cold, right?
We do as cold as possible, but we don't often get below 42. What they provide, because
Okay, but understandably, if you give us 50 degree chilled water, we can only dehumidify that airstream to probably 53.
Very limited.
And which means your store is going to be near 55, right? When we control the coil in a DX compressor standpoint, we'll drive it down as low as 35. So the colder, the better.
When I'm saying 44, 54, I'm
Mhm.
meaning in at 44, out at 54, not.
Thank you. Okay,
Sorry, because
you
your
had me a
face,
little
I'm
worried.
like, your face, from your, see, that's why it's good to have your camera. Yeah, I was giving you the inlet and outlet temperatures. So 42 to 44 is pretty normal.
Yeah. Okay. I
Coming
would
out
agree.
at 52.
Right. Yeah. Mm-hmm. Mm-hmm. Okay. Right. Yeah. So again, okay, so you're talking about the hydronic heating, or are you talking about chilled water? So, okay, so we're talking about hydronic heating then. Is that what we're talking about? Yes? Yeah.
We
So
essentially have a
you said
two-pipe system.
90 degree Fahrenheit, 200? Is that what I heard?
So essentially we have like a heat pump, or sorry, like a two-pipe system with
Mhm.
glycol coming into the building in the summer and the winter. In the summer, it's for cooling, so it's probably going to be 45 or 44 to entering, 54 leaving.
Okay.
Yeah. And then in the winter time, it's going to be about like, I think 100, 140 going in, 120 going out.
Okay.
That's
So
typically
you
Okay.
do
a
a
condo.
switch over from boiler to chiller system? Is that what you're doing? Yeah.
Yeah. So we have like an indoor air-cooled chiller on like the mechanical penthouse.
Mhm.
One of my
Okay.
questions is during the winter, will we need a dedicated cooling line?
No. Yeah. So in the winter, we don't need the cooling. So that's interesting. And I don't know,
Mm.
Barbara, if you come across this circumstance. So essentially, it's almost like when we run as a heat pump ourselves, we use this evaporator coil. I hesitate to call it an evaporator coil, the indoor coil for cooling in the summer, and in the winter we use it for heating. We use it in reverse. That's the same thing you're going to do. It's going to be a
Okay.
hydronic, and you're going to give us chilled water essentially in the summer and hot water in the winter through the same coil, correct?
Yeah.
Okay. Okay. And so, Barb and others, is there also a refrigeration rack providing us hot gas reclaim for tempering the air in the
Yes.
summer? Okay, good. Okay,
I saw that in Calvin's email anyway, that there would be reclaim for heat.
Yeah.
right, right. Okay,
That's
fabulous.
interesting. That's a very standard condo designed to have the two pipe system, but not normal for a grocery store. But we're limited
Mhm.
because it's the urban application.
Okay, no problem.
Mm.
So that's good. Yeah. Hmm.
You would need a chiller
Well,
system.
we would have to be a
Yeah.
water
Yeah.
source heat pump then, in that case, Barb, right?
We definitely we'd need our own
Right. Yeah. So
heat pump,
if you
but
give us
Yeah.
water at 90 degrees in the summer, let's say, which is kind of high, we need to then put our condenser in that flow, and we need to pump and we need to cool out of it. It's almost like outdoor air, right? At that point, and then because we need our coil down into those 40-degree or lower temperatures, or else you can't dehumidify. You can't even cool. So yeah, right. Okay. So if
okay,
that's
so
the
that
case, then we
changes this
need
too.
to.
This isn't very, yeah, good. This is
Yeah.
good. Yep.
Yeah.
Mhm.
So it becomes for us a water source heat pump, we call it, where we have a water source on our condenser. So you don't see the condenser coils up here, but they're at the top of this unit in this example. And so we will then need to have our compressors pump that cycle to cool our coil. And that's fine.
Okay. Yep.
Yeah. Yeah.
Oh, and the other thing, if it's heat pump, we can't do standard refrigerant. Oh, I guess we can when it's water source, Peter? It won't become a heat sink if it's R449 because they're not using CO2.
So that might be a problem
Yeah, we have to
on
look
the
into that.
heating
Mhm.
side. But so we'll need it for the summer for tempering potentially the air. It'll need to be there, but we may not then be able to use it for
Mhm.
well, we won't be able to use the reclaim
Reclaim.
coil for heating. we'll need to use auxiliary heat only. Yeah. Yeah. Lots of questions. Interesting. All right. Well, let me get to the next slide, which we'll talk about the heating modes, and we're getting there. It's good. So those are the different cooling and dehumidification modes. Let's go to some of the heating modes. We'll just show you what those look like. So our first heating mode that we typically like to have is where we get that free waste heat from refrigeration, right? And we call that reclaim historically in the industry. So if you have a refrigeration rack, and up here is a refrigeration rack, there's a refrigeration gas cooler or condenser over there. Typically, refrigeration systems, as you know, they have their cases that are cold, and then they dump all their waste heat out on the roof out of one of these condensers. And you have that not on the roof, I suppose. I don't know. What are you doing with the waste heat for your refrigeration system in the store? Yeah. Yeah. Perfect. Perfect. Exactly. Okay. So that's exactly what, what I'm drawing out here coming from the condenser, but it can come from the rack, or it typically comes from the rack. And so that pumps over to our unit. This is typically our first stage of heating. And it might still be, even Barb, in this project, a first stage of heating, if, because it's okay on its own. But what happens often is, in some of our systems, you guys will do some CO2 projects, I'm sure, with some of your other customers. I know Dave Bradley does. We have the opportunity in some of those projects to even get more heat. In fact, we can go as far as almost getting all of the heat that would otherwise go up to the roof to the condensing unit of the refrigeration system, and we can put it through our unit. And so when you have a CO2 system, and I know you don't for this project, but other projects when you do, we call this refrigeration source heat pump boost. We can get an enormous amount of heat. Just to give you a sense, the heat you'll get out of your HFC rack, I call it an HFC rack, or your synthetic refrigeration rack. When we do this approach, and it takes a different refrigerant, so it's not like it's an option for you right now, but we get 5 or 6 times more heat out of it. So when you guys are working with Dave on some of the CO2 projects, just know that we get an enormous amount of heat out of refrigeration systems when it's a CO2 system. But for this project, not a possibility, but that's okay. If that heat is not sufficient, we do have the option typically of putting in a water source or an air source heat pump on our other coil. And I think this is what we've been talking about here. Now, in your project's case, we can't run these two in conjunction, so we'll have to have one or the other at any one time. So we could start with reclaim, but once we need more heat and we need to go to your water source heat pump, we'll need to shut that one off and we'll need to go over to the heat pump. The reason being is they both raise to about the same temperature. And so when one's leaving temperature is the same as the other one's leaving temperature, you get no net benefit, right? Because you need to have a temperature differential across a coil. And so we'll only be able to use one or the other at any given time in the unit, but we still will need them both existing for various reasons. Lastly, if we still need more heat after these guys have been exhausted, then we still have auxiliary heater. Now, this being an indoor unit, is this going to be an electric auxiliary heater or a separate duct heater of some sort? So it all depends on the capacity and the temperatures, of course. So a heat pump, when we are in our unit, so our unit would be handling all of the outside air typically, right? And in your example, you're doing that as well. The leaving air of the water source heat pump, depending on the air volumes, might be 65 degrees, because the entering air is your freezing outside air, which is, maybe, I don't know what your design temp is here. Is it maybe minus 10 Celsius or something like that? Yeah, it's pretty cold. And so even though we're mixing it with the return air to lift it up, our entering air to the coil is still going to be, maybe 30 degrees, 35 degrees Fahrenheit. And so a heat pump can only lift that so high. And so it all depends on your water loop. It depends on a lot of variables, which Barb will work through with you guys. But we can only lift it so high. The heat reclaim coil, when it's an HFC system, can also only lift it so high because it's HFC and we don't get a lot of temperature out of HFC reclaim. And so sometimes that's still not enough, in which case then you pull on auxiliary. The other reason for auxiliary is the insurance companies like it because it's kind of the safe thing that's there. Because if your refrigeration rack is down, we don't get any reclaim, right? If your water loop is down, we don't get any water source heat pump. And so often insurance companies will still require that last stage coil at the end. So I'm assuming you're planning something of that sort. Do you know any more details about that? The electric or okay. Mm-hmm. Yep. Yep. You'd hope so. Mhm. Yeah. So this is something that we just need to work through. And of course, yeah, we'd all hope for that. And then you also have to decide, do the insurers still require you to have it as an emergency backup? Maybe you never use it, but you need to have it there. And so there's some options there. In our unit's case, just something you should know, when you have integrated auxiliary heat, that last stage, either electric or natural gas, we have to do a vertical discharge. So we supply out the bottom, which is sometimes a problem for indoor units. If we need to have a horizontal discharge coming off the side, then we don't have the ability to have that one. And so in which case you would put in like a duct heater or a separate outside heater off of that. So I don't know whether this unit needs to be horizontal in and out, or whether vertical is possible. But those are some things. There's solutions for it, but just details to be aware of.
I think we don't know the tonnage or the airflows from you yet. I think to be able to give you a size, because we've got A box, B box, C box, D box. I mean, we could show you the minimum, and I don't think you need well, we have I don't think we know enough yet.
Yeah, I think a D box 8 feet is going to be a problem, but C box might fit. Yeah, and I think there's some higher priority decisions that you need to understand to make those
First, yeah.
decisions. We have the options. If it's a horizontal unit, then you put a duct heater on, right? You just buy one, right? And in our case, if it's an internal unit, and that's in many cases, this is pretty common, we don't do natural gas integrated because it's not approved for venting in an internal
Inside,
atmosphere.
yeah.
So then you need to use a gas duct heater that are approved for that purpose. So just keep those things in mind. And okay, that makes life easier. Okay. So it could either be an electric duct heater or internal to our unit, but then you have a vertical discharge. You just have to keep that in mind. So, but we'll help you through all those details. Okay. So those are heating modes. All right, moving along here. We have till 2:30. Am I correct on that? Okay. So let me accelerate a little bit here. Just a little bit about our unit. All the quality components you'd expect. Direct drive fans, no belts or pulleys. That loses lots of energy. Those are very inefficient and have maintenance problems. The typical compressors you'd expect, Copeland compressors. All of these things, our controls are in here as well. And controls are becoming more and more important. As you guys might be aware, we're moving to new refrigerants, at least in the United States, California by code. By Sunday, we will know whether all of the United States is moving to that for 2025. And so those refrigerants are slightly flammable and they require special controls and UL certification. So more and more, we're finding that we really need to have a dedicated control for the unit that manages all that and has the UL certification as a unit. And then we just talk by Modbus, BACnet, whatever, out to the rest of the world to your BMS system. Do we have a BMS system for this? Do we know what this is in this for Kmart, HMart? They don't have one. Okay. Wow. Okay. Well, that's fine because then that means we definitely need a controller inside to take care of the unit and let it run and do its thing. So that's no problem as well. But if that ever changes, that's what that device does. It talks to the outside world as well and makes that work. So those are the things you would expect from a unit construction. These are very high quality units. So I'm sorry. They're manufactured in Tulsa. Yep, and assembled down in Tulsa in the U.S. Yep, they do. Yes. Yep. Barb.
So when they have CO2 reclaim coils in them, it's usually around 28 to 30 weeks lead time. When it's refrigeration heat reclaim, it's 26 to 28. It's coming down a little bit, but still planned for 26 to 28 weeks. Yeah.
Absolutely. I always ask Barb to ask the questions that are the hard answers. I take the easy ones. So if they're hard, then I refer.
The ones that people might get upset about.
Yeah, that's right. I just take the easy ones. Absolutely. Right. um, All right. So just our offering, just so you guys are aware, I don't want people to be misunderstood. We've been showing you images of packaged rooftop units, but as we just talked about, we do split systems. This is actually quite rare in our space. So we get a lot of projects because people need split systems, and then makeup air, chilled water, whatever the case may be. So we do makeup air units. It's not something that people ask from us a lot because they just like their kind of cheap and dirty ones. But we can do pretty much any kind of unit you want in that world. And our range of size 6 to 140 tons. Generally, our sales are run between this kind of up to as much as 70 tons. Very few people go into those ultra huge because those are ultra big units. But we can do these technologies in a very large range of units.
And I'll just say this too: in the past, with our older style units, you guys are going to come across on the superstores 100-ton units, 120-ton units of ours. We do try and cap it at 70. It's a much smaller unit. It's kind of the sweet spot of efficiency for the superstores. So what we're working on with Dave is, I know sometimes the ductwork is oversized for a smaller unit, but a lot of times the load in the store has also, we don't need so much as what it was originally designed. So we do like to cap it at 70 just for your.
Yeah. And look at the weight difference. I mean, you look at that, that's 6,300
Huge.
pounds. It jumps to 12,000 right away. You just get a sense of this thing becomes one of those monster things that you see on
School
roofs
bus.
out
Almost.
there. Absolutely. So multiple units is better when you're getting into these ranges.
Yeah.
Okay. So benefits, some of the things we've been talking about. We consolidate the benefits of all those other technologies synergistically into one unit. We consolidate outdoor air and indoor air and still provide great mixing and distribution. So instead of having a DOAS unit that's just dropping in outside air over in the corner, ventilation air, and then recirculating units everywhere else, because we're pulling that together, we're doing that and spreading that outdoor air more broadly through the store. Walmart during the pandemic came to us and said, I don't want to bring in more outside air, but I want that ventilation air distributed more broadly through my store. And so that consolidation gives them that advantage. We consolidate other technologies like heat reclaim, heat pump technologies. The more that you can bring these into single units, and I'm not saying that you only want one unit in a store, but the more you consolidate your units into fewer, the more you can take advantage of these technologies. If you have a lot of units that all have tiny little bits of airflow, you really can't make advantage of heat reclaim and things like this. And you're spending a lot of money. So this is another thing it does. Consolidates and reduces the tonnage and cooling and roof weight. Consolidates first cost because you have less equipment to pipe to, electrical hookups, breakers, service, all of these different things. Consolidates maintenance cost, and it consolidates embodied carbon. Embodied carbon being the new phrase that's being talked about in the meetings I was in last week down in Baltimore, which is near Washington, D.C. This is what they're talking about, is the next wave of carbon reduction. How do we limit how much carbon is consumed in the production of the things that go into the building and the transportation of the things to the construction site, not just how much carbon the building creates while it operates. So it's now all the materials going into the building, not just the building itself as it operates through time. And of course, if you're consolidating HVAC units, you got less compressors, less fans, less pulleys, less sheet metal, less refrigerant. Our unit typically uses half as much refrigerant as all of our competitors that are out there in the market as well. And refrigerant isn't really a good thing. We'd rather not have more synthetic refrigerant than we need. So these are some of the benefits of what we do. Now, as you guys may remember, our company used to be called CES. Looking at this slide, does anybody know what the C in CES stood for?
Consolidate.
Wow, I got a sharp one here. Yay. You wouldn't believe how many people stare at the screen and go, no idea. No idea. Good.
Well,
Excellent.
It's bold, it's capital. Like, how could you not know?
You know what? I'll invite you to make fun of them the next time I do one of those.
Sure, I have no problem with that. No
So
problem at
again,
all.
in simple terms, what is a DOAS Plus? It's DOAS and RTU together, really is. And these are products that are out there all over the world, and this is what we do. So here's a simple example just to drive some of this home. This is a store where they installed, the design was for a 25-ton DOAS, bringing in 3,000 CFM of outside air. Again, it's a DOAS, so only outside air coming through that unit. And then they had two 6-ton Lennox RTUs on the roof as well. So given what we've talked about and the idea of consolidation, there's the key word. If you had our product, our DOAS Plus with adaptive multipath at your disposal, how could you improve this design?
You would basically not have the two RTUs, and you'd have your DOAS Plus, and it would probably jump up maybe to 30 ton.
Wow, have you seen this slide before?
No, just taking a stab at my previous
That's
projects and
impressive.
such that I've worked on.
Nicely done. Nicely done.
Mm.
Anybody less
Just
aggressive
trying to
than
learn.
Dimitri? Yeah.
Yeah.
I mean, we don't usually get that as the first answer. What would be something in between maybe you could do? But I like that answer.
In between,
Yeah.
maybe, well, there's many different things. You can probably remove one 6-ton RTU and keep the other one, depending on what it's serving exactly. And the DOAS would probably reduce to 20.
Okay. All right. Thank you. All right. So here's the two scenarios. You're right on. So we can put in a 25-ton DOAS Plus and eliminate one RTU just for free. So this is a demonstration of the point that you take a 25-ton DOAS and you make it a 25-ton DOAS Plus, you get 6 tons of free cooling. In this case, this is actually in Texas, the store. So in their environment, we get 6 tons of free cooling in our 25-ton box. All the same airflow, same amount of outside air, same amount of recirculating air. We haven't changed anything but consolidated into a DOAS Plus. So that's the easiest, most straightforward one. But Dimitri, I like what you were saying there, because this is maybe another option, is to consolidate them all into one. But you're absolutely right. I don't get 12 tons of free cooling. There is a limit to this. So in which case I need to upsize this. So in truth, it turns out I get what? 20, 37. I get truly 7 tons of free cooling in my 30-ton unit.
Yeah, because you mentioned in the beginning, like you can remove 6 tons.
Glad you were listening. I said that for a reason. Nice.
Yeah, it's really interesting.
You make me happy. All right.
I'd love to see this. I'd love to see the DOAS Plus though on a psychrometric chart.
Oh, that was back up there.
I saw the charts, but I want to see it all consolidated into it. Because you said I'm not going to put this into a chart. I'm just going to show you this wonderful
with the DOAS Plus with
picture with all
adaptive
the
multipath.
buttons.
Oh, and I can do that, yes, but I have to do it for each mode of operation, of course, because it changes for every mode.
Yeah,
Yes.
I figured. No, that's really interesting. I like it.
Good.
It's
Good.
It's good.
Right.
This has been actually a very good presentation.
Well, thank you very much. Appreciate that. So, you guys, that's the most aggressive approach. And here's the savings: 20% tonnage reduction, 55% weight reduction when you consolidate all those units. In this project, it would save them $30,000 in the construction labor, all the hookups, the electrical, piping, natural gas. Obviously, we get better space conditions, and we have the option for heat reclaim and air source heat pump, or in your case, water source heat pump. So really gives a lot of opportunity there. So it's just a very simple example. All right, zipping along to electrification. This is the big thing for everybody, all of your customers, all of our customers. And we talk to them almost weekly about their electrification strategies that are going on. And, these are different terms that are thrown around. Ultimately, what it comes down to for us in the HVAC space is decarbonization, how to get away from our natural gas auxiliary heat, our demand for that. If we can do that, then we enable all of these other goals that these companies have. And so the first one, of course, we all like heat pumps. And I'm sure you use many, many heat pumps. You have them designed in this already. A heat pump, by definition, is something that essentially pumps heat from one place to another using a compressor to do some sort of lift. A lot of us think of heat pumps as air conditioning units that can run in reverse. But in reality, an air conditioning unit is a heat pump. It's pumping, heat out of a store, putting it out into the outside. Or you can have heat pumps that are just doing heating. And there are heat pumps on the market. All they do is heating. They don't reverse. So something to keep in mind. But that's how heat pumps work. And so we have multi-source heat pump technologies. We have water source heat pump. We have air source heat pump. We have ground source heat pump. And we have refrigeration source heat pump. Now, refrigeration source heat pump, you would consider or think of as reclaim, right? Or reclaim like you're doing in this case. But in truth, it is a heat pump as well. One of the reasons I want you to start thinking about it in that way is that regulatory bodies, government rebates, and insurance companies all like the word heat pump. None of them know what reclaim is. They don't have the first clue because we only use it in the grocery industry. And so it is a heat pump. It is a compressor that is moving heat from cases to a exhaust point, and we're just tapping into that. And so by using this term, you get better acceptance of the concept and the technology. So if you get to the point where you want to remove your auxiliary heat altogether because you're hoping we can get enough heat from these other sources, these are the terms to use because they will help a lot. And technically it is valid. So that's the different type of them. One thing to watch out on air source limitations, we're not talking about that for this project. You can't have a water source heat pump or an air source heat pump operating while you're dehumidifying, right? Because you can't run forward and reverse at the same time. So a lot of people along the Gulf Coast, it is actually cold but humid, and they want their heat pump to run, and it just never turns on because they're in dehumidification mode. So that's just something, not that it will affect to us. Sufficiency drops, of course, below 35. We have a great frost problem right around freezing. Frost only occurs 9 degrees above freezing and 9 degrees below freezing. Below that, we don't get frost, not enough moisture in the air. And of course, above that, we're not at cold temperatures to frost. And of course, outdoor air units have real big challenges when we're talking about air source heat pumps, just because that cold air coming into the coil pushes us outside of our compressor envelope, and we have to shut down the unit. So that's something to keep in mind. Those DOAS manufacturers, one of them was speaking at the conference last year that I was at. And so it's a DOAS, it's a dedicated outdoor air unit, bringing in only outside air. Somebody in the audience asked them, what's the lowest temperature your heat pump will operate to? I don't know, what kind of temperature are you guys seeing right now for heat pumps? Like the lowest operational point before they shut off? Do you have? Mm-hmm. Okay, -4. Sure, right. That's -4 Fahrenheit. Okay, all right. C, okay, -4
Is
C.
that
Okay.
when they include an ERV? Do you know, Calvin? Just
Actually,
curious.
mhm. Outside air. Mhm. Right, right. Okay, so that would be -4 Fahrenheit, because if it was -4 Celsius, that would be like 28 Fahrenheit. And every heat pump to actually qualify as a heat pump has to run at 17 and 47. Those are the two rating points. So I think that's -4 Fahrenheit, which is better. But that's probably where it's rated at. And so some of the, sorry, Calvin, go ahead. hmm Part of the conversation that Barb was bringing up is almost all of those ratings are when those units are only recirculating, because the warm air, it needs that warm recirculating air to keep it running. So a DOAS unit that is just outside air, this question got asked of this manufacturer, they shut down at 45 degrees Fahrenheit. That's the coldest they can get, because that indoor coil has to have a relatively warm entering air temperature. So if it's recirculating, happy as punch, it's getting 75 degrees. It loves that. But as soon as you bring in outside air onto these heat pumps, they really struggle. And if it's all outside air, like a DOAS, then they actually don't qualify as heat pumps because they can't run at that 17-degree rating point. And so knowing that concept, we're living in between, right? We're bringing in outside air because we have to, but because we're also bringing in recirculation air, we actually temper that air so we can keep our heat pump running longer and lower temperatures. But watch your rating sheets. We see it every day of the week, heat pumps only providing the recirculation value. And of course, they have great low temperatures. But as soon as you put outside air on them, those numbers fall apart. So just keep your eye on that very carefully. Okay. We make those units too. So that's why we understand it so well. So that's one technology. Just one thing I want to clarify the difference between reheat, and I heard Jerome mention reheat at the beginning of the presentation. Reheat is when we get waste heat from our own compressors as an HVAC unit and use that to temper our dehumidified air, right? And it only happens when we're doing dehumidification because our compressor is running. Whereas when we're talking about a refrigeration source heat pump, or what we were calling reclaim, it's waste heat from the refrigeration unit's compressors. And so we get it year round. We get it for dehumidification and we get it for heating. And so it's a great source of heat. It's way more heat than we generate, and we can use it for year-round operation. So this is why we are so happy about that. And refrigeration source heat pump does not care about the entering air temperature. In fact, the colder the air that hits that coil, the more heat it gives us. So, because we want a high delta T. So it's kind of opposite from all the other heat pump rules that you may know in your mind. We love outside air on this type of technology. Jerome's not, you're on mute.
Oh no, I'm just reading to myself.
Oh,
Sorry.
you're just leaning in and reading. All right, no problem.
Yeah,
All right. So just something to keep in mind the difference. Obviously, if we don't have a refrigeration system, you have no choice but to use reheat. You got to get that from somewhere. And of course, you'll be using that in a lot of your projects. But almost all of our projects are going this other way because we have this great source of heat from the refrigeration system. Okay. All right, so some of the strategies for that is, of course, our approach maximizes that utilization. We factory install those coils, and we can do your HFC, synthetic refrigerants, glycol fluid, as you're doing, talking about HFOs and CO2, CO2 being the very best refrigerant for this. Just to give you a sense, some of the temperatures we get out of like your 449 refrigerant on a reclaim, we probably get like 160 Fahrenheit. With CO2, we're well into the 200 degrees Fahrenheit realm. So really, really high quality heat that we get from CO2 racks. It's really great that almost everybody in Canada does CO2 refrigeration. It's a big benefit. All right. So let me see, what else we got to talk about here? I think that's about it. We're out of time. Any questions to this point? We have so many more things to talk to you guys about. But I don't know if they're necessary for what you're doing right now in this project, but we have some special technology for ERVs. We call it multi-stream ERV. We have a technology that was the next slides where when it's a CO2 refrigeration system, we can provide energy benefit back to the rack. So it will benefit us for heating, but we can provide benefit to make the refrigeration system more efficient. We call that multi-flow reclaim. We have all these multi-technologies. I'm thinking of calling it the multiverse. I don't know. What do you think about that, Barb? Flo's multiverse.
Oh, please don't.
Peter.
Don't call it that?
Please don't.
Okay.
You're just gonna mix it up with Marvel, and I'm gonna get confused.
I know.
And then I'll be thinking about this all the time instead of Marvel movies.
Awesome.
No,
Okay, we see that. Okay, it's done. That's it. That's the clincher. If that is my goal. But any questions? I think before we close this session off, I think this is the basics of what we do, and as they apply probably to this project.
I do, but I can wait till everyone else.
Okay.
Because it's not. Yeah.
Mm-hmm. Mm-hmm. So what are our what requirements?
Clearance.
Service clearance.
Oh, right. Barb, you probably know that best. That's another hard question. I'm not going to answer it.
I know. Well, it depends too. If it's water cooled, we don't really have so much more other than in front of the control panel and the sides. If it's air cooled, then nothing can be on top of it. So it wouldn't be inside anyway. We've got, I guess the clearances, I don't know off the top of my head. I'm sorry. We've got them on every single submittal when we show you dimensional drawings. Once we send that, there'll be a little box on the top left and it'll show you service clearance requirements around the unit. So the important one is in front of the control panel. You have to be able to open the door, obviously, and there's electrical codes that require, I think, space in front. Yeah. That's the most important.
Calvin, are you guys using Revit for any of these designs? Okay. Okay. Okay, we have Revit models, and our family models actually have the clearance envelope drawn on them to show you where your clearances are for your Revit designs. So we can get you those models for your library, at any time. But that's another way to look at it. But yeah, as Barb said, our submittals and our drawings show you the clearance numbers that you require. No, I think it's okay. I think it's probably, yeah. Mhm. So the outdoor air is fixed. It's at the top at the end. The return air can come from the bottom or the same side as the outside air. So right below the outside air entry as a horizontal intake. We can't do side on that. And then the discharge, I want to say it's side and also at the back. But what do you say, Barb? Maybe it
Yep,
depends.
we could do side, or it's for us, it's a special, so it's custom, so it is a little more expensive to do side discharge. But yeah, it depends on the configuration where we have to put heat reclaim, heat. So it's kind of hard to say, but occasionally if it's an air source or if it's an air cooled unit, for example, we can bring the air out the side.
That'd be great. Oh, that would be great.
Oh, no, you're not wasting my time. Don't worry. This was really good. Really informative, actually.
Thank you.
Going back to that slide, that last page, and you're talking about the CO2 refrigerant
Mm-hmm.
tying into the DOAS Plus units or these
Yeah, do you want to bring
units.
it back up? Mm-hmm.
How does the system know? Like, okay, this question might be hard for me to ask, but how does the system know that you're putting the CO2 into the coil, into your reclaim coil, and that unit's constantly running, but how does it know when it can't take out any more heat from that CO2 system? Like, is there any point where it needs to shut off? Does it know how to shut off and not utilize the CO2 or reclaim,
So,
like depending on
yeah.
how the time of day and for the store? Like, I'm just curious.
Yeah, so the controls work on a couple things. You know, the most simple level is we're watching the store's temperature, right? And the source
Hmm.
humidity, of course. And so we're watching how it responds to things that we do. And we're not only looking at what it's at, but we're looking at the rate at which it's changing. And so if we see it changing at a certain rate, we can respond more aggressively to try and that's at standard control group, just like, all controls exist.
Yeah,
But most people just look at the value. We're also looking at the rate of change to try and make some of those decisions. And really then it's just a matter of how does the space respond to what we're doing. So if the space temperature is sinking very slowly, then we can bring on a little bit of, of heat. Now reclaim is special in that today, up till now, it's always been an on-off binary thing. We get it or we don't get it. And so
okay.
then we have to essentially pulse width kind of manage that on that scenario. Something that we're about to start doing with our new technology is we're going to start modulating that as well,
Oh, really?
and doing control of that. So then we can control what it's giving us. Obviously, you can imagine a CO2 coil when a system, refrigeration system is running maybe in transcritical, it can give us like 270-degree refrigerant. So we kind of want to manage that a little bit more. Right now, we just turn it on and off to get what we need.
I see. Okay.
Yeah.
And
So that was
then
that one.
when it's off, it'll reject it into the condensing units outside.
Yeah, that's
Yeah,
right.
okay. That's good.
right.
That's really that's
Yeah.
good to know.
Yeah.
And did you
Thank
mention the set point for reclaim is kind of in the middle, like so it will stage on as the first stage of heat?
Yeah. I didn't really, you're right. So
Oh.
it is our first because it's free heat. That's our first stage of heat.
Mhm.
If we were to put in a heat pump, and so your question gets much more complicated
Yeah.
because
As you go
yeah,
on, yeah.
because you have this reclaim coil as your first stage, and then you bring on this reheat coil, or sorry, not reheat, heat pump coil, which is second stage, but comes before the reclaim coil in the flow direct, right? And you look at this, the stacking up of them. And so then what happens is we have to manage, we want to maximize our free heat, but we want to slowly bring on this heat pump heat. And so we have to manage that very carefully because if you're bringing that on too much, you actually take away what waste heat you can get or the free heat that you get.
From the
And so
CO2.
this is
Yeah.
the sophistication. This is what we do. This is, we're a company that
It's
does
really cool.
controls and the sophisticated control to make it simple. The customer never sees this. The BMS never sees it. It just says, I need heat, and we take care of all the rest of it. And then the same thing is the last with the auxiliary, like you would think. After that, if we still don't have enough heat, then we start bringing on our stages of auxiliary heat. And then we're watching always the space.
Okay.
Yeah.
All right. Thank you.
It's lots of fun.
Yeah, it sounds like it.
Yeah.
It's really interesting.
Well, good. Good. The heat pumps are incredibly complicated and interesting as well. Yeah. Yeah. And as you can imagine, when we start putting in DCV and controlling our outdoor air ratios and reducing that, the entering air temperatures change for all of these coils. And so their performance immediately changes as well. And so then everything has to be recalculated and refigured out how we're going to optimize all of these different sources of heat.
And how to work together. Yep.
Yeah. It's kind of cool.
It's good.
Any other
That's
questions?
it for me.
All right.
I had a question just about so I'm looking at our system for HMART and then our CES unit that we're going to try to plan out. So before we were talking about temperatures and whatnot, and Calvin was saying that it was 90 Fahrenheit, 100 Fahrenheit leaving, and that's correct and everything. What my question is regarding on the dehumidification process. To get that, we're going to need lower temperature fluid side. Is that correct?
So we have two choices. If you're going to give us
Yeah.
what we call a chilled water coil, where you're putting water to our coil, it needs to be cold enough to dehumidify. If you can't give us that, then what you do instead is you're giving it to us to our condenser, and we're adding compressors and we're driving that down to what we need, almost like an air source, a standard package unit. So you're doing water-cooled condenser and a water source heat pump in our unit to make that happen if you can't give us cold enough temperatures.
So will the condenser require refrigerant?
No, just on our side, we would have our compressor and our refrigerant, but then you cool it with water. It's in a water pipe. What is it, Barb? How do you describe that better?
Water pipe. Yep.
Yeah. So instead of an air condenser, it becomes a condenser in water.
What I haven't seen though, I haven't seen that done with the two pipe system where it would go condenser or heating. I don't know how that would be.
It's kind of cool actually, because it makes the water source heat pump really good.
Exactly. But because we've always had dedicated piping to the condenser and hydronic heating. So I'm not sure how we would figure out. We'd have to be a little bit careful with if it's an either or situation of how that's controlled. Because if you ever suddenly have a dehumidification need, we can't really run the compressors if there's no water coming to the condensers to cool that down. So that'd be
or if they're heating that water and we're trying to cool the air.
That could be a problem also. So that will require some control strategy involving and
For sure.
Does that make sense, Jerome, how I described how we need to work that? Yeah.
Okay. Yeah, no, that makes perfect sense. What I'm wondering as well is, since this is an indoor unit, do we have to worry about the safety of the refrigerant leaks or things like that? Does it need to be contained in a room?
No.
Okay.
No, especially when you're using HFC refrigerants, you're using low pressure refrigerants on the refrigeration side. Ours are the similar pressure. I think, kind of 500 PSI is the extreme high. So you're not worried about that. But even if it was CO2, which can get up to 1800 PSI, that's something we do very commonly.
They're ceiling hung in or on platforms in supermarkets all the time. Yeah, it's not like a mechanical room requirement and all that stuff. It's not.
Okay. Yeah, that answers my questions then.
No, that's good questions. Good. Yeah, great.
Oh dear. I actually
had to go a long time ago.
I know. I have another meeting that started at 2:30. What are your thoughts for the HMART review? Oh, okay.
You have time, Barb, to stick through this right now?
Yeah, I'm just gonna I don't want to miss it.
Right. Yes.
Yep.
Right. Yeah. Yeah. Yeah, so because our unit needs to operate itself without any other inputs, and we do this anyway, we need to watch the space conditions. So that will come with the unit, and the contractor will mount it below the unit and wire it up to the unit.
So the reason that's there is because a lot of times with different stores, when they want microthermal, they want 2 sets of sensors and they take an average. When it's iController, they want 1 set of sensors and that's fine. So really it was just, we want to know, are you good with 1 set of combo sensors? And that will be in the submittal anyway, but that's just really why that was,
I see.
that was
Okay.
there. Yeah. I almost want to say maybe this might be a good opportunity for 2 sets and then take an average. What do you think, Peter? We don't want it near any airflows, airstreams, or open cases. So centrally located is usually really good. But again, maybe this one, since there's a few different zones, might benefit from 2 and taking an average.
Yeah, I mean, I can't remember all the duct work, but obviously our unit's responsible where the duct work goes. Otherwise, there's nothing else we can influence. So whatever gives us the right, I mean, it's really just taking the right reading for the area you're trying to control. If that.
Yeah. Sure. Mhm. Oh, yes. Yep. We'll include 1 for now. You can add yep, that's. And
Yeah.
this is really for us, like, would our unit be 575, 360 or 208, 360? That's what we really want to know. Yeah. Sorry. So which one is the site voltage? Is it 600 or 208?
Yeah. Right. Yeah.
Okay.
Yeah.
So maybe
it's
on this we'd prefer 575 because it is more expensive when you have the 208. Oh yeah. Yeah, it will be. Yeah. Okay.
Yeah.
For sure, it will be.
It will
over
be.
2 horsepower.
Yep.
Hmm. So what you want to look at there is kind of, I mean, it's about the rate at which we have to remove heat or or condition a space. What's the square footage of your sales floor area that this unit would be responsible for, approximately? Okay. And so the sales floor area, is that the same, or is that like there's always back of house and yeah? Oh,
Okay.
18,000. Okay, 18,000. Okay. How would you advise on that, Barb?
Yeah, so it's the entrance vestibule separated from the sales area.
Looks like it. Yeah.
Yeah.
Yeah, it is.
And then you have other heat pumps for the kitchen area. HV. So I would almost say where you have that it's zoned CES, wouldn't we just consider the 18,000 square foot, Peter?
Yeah, I think so, absolutely.
There
I'm just
might
trying
be
to
the
remember.
grocery deli. No, that's still another heat pump too. Yeah.
Yeah. I would imagine your selection tool kind of guides you guys based on your heat, your essentially your loads, because that's really what it is. It's a relationship to what's your airflow needed to the load that you're trying to accommodate. What we see in grocery, and I think Dave does this typically, I think he sits at around, because again, I don't know all the loads, you do, but a 0.75 CFM per square foot, we often find just because grocery stores are typically always the same in the end, right? It's always the same kind of loads. That ends up being kind of a rule of thumb of where we land. So if it's 8, yeah, that would probably be about right. Ideally, we want, a 50-50 ratio there of outside air to return air, and that sits nicely. What do you think, Barb? That looks like a good ratio.
Yep, 15.5. And we can go down, just so you guys know, to 0.6, 0.58 CFM per square foot, but Peter gave you a good average, I think, of what Dave's comfortable with.
But your load analysis will give you a sense of that, right? Because if you're not circulating enough air, not treating enough air, you're going to lose control. So,
outside air is,
that's the technical driver of it, but the rule of thumb, I think, ends up being there. Yeah. Right. Okay. Oh, perfect. Right. Okay, great.
That depends on your ductwork. Yeah.
Which looks like it's extensive.
It looks like there's a lot.
Probably more than I've ever seen. Mm-hmm. Oh, so we've lost our outside air? Okay, good. Mm-hmm. Yeah. Mm-hmm.
And also, what size ductwork are you? Because now that you've determined 13.5 CFM of supply air, you guys will need to just determine the diameters and how many diffusers you're going to put in there. And then we know more about the static pressure you want us to size around. Well, normally if people are using diffusers, it's a lot lower. We can get away with 1 inch or 1.5 inch, but you guys have a lot more. So I wouldn't say but I would probably guess you're going to be around 2 or more inch.
Yep.
Sure. Yep.
No, I'm good.
Not yet.
Okay.
I think
What's the?
something, oh, sorry.
Go ahead. No, Barb. You're
I
probably
think
going to
we're
ask the
going
same
to ask
question
the
as I am.
exact same
Mm-hmm.
question. We need to make sure that the run is not more than 90 feet from where the protocol is to our reclaim connection. So that's 90-foot maximum when it's refrigerant.
Yeah. Pressure drop, temperature drop, bunch of things.
It's going to negatively affect your rack, and we don't want to do that.
I don't think we're gonna meet that 90 feet
Oh yeah.
maximum. I think we're like, oh yeah.
Shoot.
By how much? You're at 1, 2. Yeah, that's excessive when it's not CO2. If it was CO2, we'd say okay, but maybe we could relocate your unit a little bit closer. Is that possible? Yep.
Mm-hmm.
Yep.
Can it? I mean, are you? Yeah. I mean, ultimately, it's the refrigeration rack guys that tell us. It's the pressure drop, it's the temperature drop, and it's the receiver sizing of the rack. Because the more refrigerant that's floating around, the more the receiver has to manage that excess capacity. So, but I think if you can move it centrally, I mean, is there a limitation keeping you from hanging that unit in the center of the sales floor, up in the roof, or is that not? Is there no headroom up in the sales floor area? Oh, and open all the way? Mm. Okay. Okay. So that's a problem. I see. Right.
Mm.
Mm-hmm. Okay.
If we don't have the plans, we don't know anyway.
Okay. Sometimes there's multiple racks, right?
Yeah.
But there's only one.
So that's it. Yeah, when you don't have the makeup air units dedicated over like you do that you've shown us, then a lot of times they might want us to interlock with the exhaust fans, so that when your exhaust fans are off, we can adjust our outside air. But you don't, if that's not needed, then you can just say no. Yeah.
You can still do it for the seafood department, though, Barb, at
Yeah. Oh, yeah,
1500.
yeah. I forgot about that. Thank you. Yeah. So if you want it, we can. That's right. Okay. Yep, that's good. We'd need to know that too for programming purposes for iController. And I'm not sure, do you know, Peter, what the maximum amount? Like I know we can do one set. We'd probably take the bigger one. I don't think we could take multiple.
Yeah, I don't know if we can do multiple.
Yeah.
Especially when there's no BMS, when there's a microthermal system, they can do the
Yeah.
math and then tell us. But without that, it's a little simpler. Yeah, we might just pick the bigger of the two, maybe. Yeah. And of course, we've got to look to see that we never get below your IAQ requirements as well.
Mhm.
So sometimes you don't have this latitude because you need the ventilation for other reasons. But definitely, we should look at it.
And you said hydronic heating as well? That it would switch? No.
Yeah. Yeah. Hmm. Hmm. Sorry. 90 supply and 100 return in the summertime.
If I may
Entering.
ask, Kelvin, how is the condos above? How are they doing cooling in the spaces?
But I
But
thought
do
you
they
said
have
it
a
was a two pipe, yeah.
yeah, do they have a refrigerant circuit in these heat pumps? That's what I'm kind of wondering how they cool, how they're cooling. How are they calling for cooling?
Yeah.
Like something when I was looking at this, just sort of in between the presentation, it was something seemed odd and off.
Well, I'll tell you, you know what's interesting is the fluid cooler tower looks reasonable because your tower can only cool it to your ambient. And that's a 90. That would make sense. Your peak ambient in Toronto is probably 90. But an actual fluid cooler device that's pumping and compressing using energy, those are the same values as your fluid cooler up above, aren't they? 100 entering and 90 leaving. It's the same as your fluid cooler on your roof. So I would suggest those numbers are wrong because the fluid cooler is doing nothing then.
Mm-hmm.
Like the pump is not, there's no chilling going on at all.
Unless well, you just be rejecting heat.
But that's
Right.
what the rooftop
Right.
unit's doing. But that's what the,
Right.
You
on the
mean
roof
100 to 90 and
up
90 to
there,
100?
the tower A is doing that. So normally that's the case, right? You have a tower that dumps the heat, and then we heat pump out of whatever we get back, whatever we're lucky to get back, 90 degrees or whatever. But if you've got actually a compressing unit chilling plant of some sort, these values it says is not actually operating. So I think those numbers are wrong. I think it is bringing it down, right? Because otherwise it has no purpose.
Something's missing.
Yeah. Fluid cooler controller. Yeah. Yeah.
You have AC units. Oh, okay. I see.
Well, on the base building, they probably use some other equipment that's not just like a fluid cooler.
Maybe.
And this project, was it done by us?
Yeah, it was.
I realize. Okay. Okay.
I'm just like as you're entering air, 75.
Yeah, these are all free
Oh.
air and and they're all the miscellaneous spaces,
Okay.
comm
I
rooms,
see.
electrical
Okay.
room.
Oh, I see. That's what we're looking at there. Okay, not the fluid. Makeup package with gallon tank. And that's a tower as well. Oh, that's on the tower, is it? Heat pump glycol fill tower.
I think maybe you guys have to talk to them and see.
It just looks like a typo, almost. That's all.
Or missing information.
Yeah. That. Yeah. I mean, so obviously, if you send us a 90-degree water for us to condense into when we're running an AC, that's like the hottest day, right, of an air-cooled condenser. So we're going to struggle, even though you've got a chiller running. It'll do it, but you're like putting it on the hottest day all the time. It would almost you just wonder whether that's. I think that number's too. I don't think it's what it actually is providing, perhaps. But we can deal with it if we have to. Yeah, please. Yeah. Yeah. Yeah.
Okay. And then that bottom one, it would, if you do, just verify if you want ceiling hung or if it will be on a platform, just so we know what kind of connections you're going to need. Yeah. Perfect.
Okay. And
This
no
is very,
burglar,
very helpful. We appreciate.
no burglar bars, huh? Don't want you breaking into the unit.
So it's going to be horizontal connections for the unit?
On a platform, yeah.
Like
so there goes the heat.
Mm-hmm. Mm-hmm. Mm. Okay.
Okay, so that's all windowed right there.
Wow. Wow. Man, our logo could be like just right there looking at the front window. Everybody could see. I don't think that would be okay. Yeah, but let's see. Yeah. Well, that looks cool. That looks a great project. Okay, not far from the office. Yeah, our office is down at Young and Davis. That's gonna look great.
Oh, the 4010. Now we know 40. We can send you the D-box dimensions. Yep. And then you'll see from it the clearance requirements around it too. Yep. Oh, here we. Dee, do you want to do a snapshot and get this?
Yeah, just
Yeah,
give me a
thank
second.
you.
Let me do a snapshot.
And just I guess remember that these are permit preliminary numbers,
Yeah.
right? And so we should keep that in our records so that we're not assuming this is always a fixed
The be
condition.
all end all. Mhm.
Yeah. Especially the ESP, because we can reduce our fan size when we get a better number for that.
Yeah.
That's a high.
These could be worst case. Yep.
Yeah. Okay. Yeah, no problem. Yeah. Yeah, of course. Looks like a fun project. That's awesome,
I
guys.
have a question. If for this, say, this style that's happening with this project, can you connect a remote condensing unit to that unit essentially, and just run your refrigerant piping? That's it, right?
Yeah.
To
Yeah.
achieve your cooling.
Yeah.
Okay. I'm just curious, not in terms of your project, Kelvin. Just it was just like a general question. Just was wondering, right?
Right. Well, and in all truth, other than capital cost, if those base building numbers are right and we're getting 90-degree fluid, you'd be way better with a gas cooler because that's only one day of the year it's ever going to be that hot, probably. So other than capital cost, yeah, you'd get way more efficiency if you ran it on its own condenser that was seeing, normal ambience, right?
Mm-hmm.
Yeah. That's pretty typical. But
Okay.
where do you put that condenser is your question, right?
That was just a question.
Yeah,
Just a general
absolutely.
question. Just wondering how
Yep.
different systems we can
Geothermal.
do. I
Yeah.
was going to ask actually about geothermal.
Mhm.
Have you ever done? Well,
Mhm.
you have. Okay, that's
Because
cool.
to us, it's water. It's just a water source, right?
Mhm.
Somebody else has
Yep.
to worry about the glycol and the pump and everything else. So for us, it's just another water source condensing type approach.
Yeah. No, I hear you. Yep.
Mm-hmm. No, that's good.
You guys should come in for lunch and learn and feed us. I mean, teach us.
Now we know the
Dimitri,
truth.
our office is not far too, and we have a bakery
Oh, I know.
attached.
Really?
I keep
Yeah.
a
yeah.
bakery,
see,
so we can feed you
It's a
there
good
too.
bakery. And if it's just food,
Temptations,
we could just get
jeez.
food together. We don't actually have to teach you anything. That's okay. too.
No, but this stuff is really good to know. Like, even like I didn't even know any of the items you brought up about the heat inside the space inside a food store and the percentages and like the outside air and then infiltration and people like that stuff not many people really know. It's actually was really good and really
Thank you.
informative.
Great.
Yeah.
Yeah.
You're right. That's
Yeah.
why we only do that.
Yeah. And there's probably only 4 MEP firms in Canada that know how to do this too, in total.
No, just
Like
one.
you guys are learning a unique
Just
skill.
one.
Nope, just one. Just one.
Sorry, there's more. You're the best.
Just
Dave's
Dave.
the best. Tell
Just
Dave Bradley he's the best at it though.
Dave is the most knowledgeable.
I think we would agree with that actually.
Yeah.
Trying to absorb as much as I can from him.
Do that. Yeah. Yeah.
All right. Well, thank
All right,
you
guys. Hey,
and
thank you so much for
Peter.
all your time. It was really a privilege and nice chatting with you guys.
Oh, thank you.
Yeah, thank
Happy
you very much.
Thanksgiving.
Thanks,
Happy
everyone.
Yeah.
Thanksgiving. Have a good weekend,
Bye-bye.
everyone.
You too.
Enjoy the
Thank
long
you.
weekend.
Yeah, you too.
Bye bye.
Bye.